Have you ever noticed that some chemical reactions happen in a flash, like lighting a match, while others, like iron rusting, take days or even weeks? Why such a wide range of reaction speeds? The reason lies in the factors that govern how fast or slow a reaction occurs, and understanding these factors is essential for everything from industrial chemistry to medicine. The rate of a reaction depends on a variety of factors, including the concentration of reactants, the temperature of the system, the use of catalysts, surface area of solid reactants, and for gases, the pressure. All of these influence how frequently and how effectively molecules collide with each other. According to the collision theory, a chemical reaction happens only when reactant particles collide with the right orientation and enough energy to overcome the activation barrier. As we explore each of these factors, you'll begin to see how chemistry allows us to tune reaction speed, sometimes to make it faster, other times to slow it down.
Let's begin with a simple yet powerful factor: concentration. Imagine a crowded dance floor versus an empty one. The more dancers there are, the more likely they are to bump into each other. It's the same in chemistry. When the concentration of reactants increases, there are more molecules in a given volume, which leads to more collisions per second. And more collisions means a faster reaction. For example, consider the reaction between hydrochloric acid and zinc metal. If you use dilute hydrochloric acid, hydrogen gas forms slowly. But with concentrated HCl, you get a much faster and fizzier reaction. Mathematically, this relationship is expressed as rate is proportional to the concentration of the reactant raised to the power n, where n is the order of the reaction. On the graph you see, notice how increasing the concentration steepens the rate curve. This is direct evidence of faster product formation due to more frequent molecular collisions. Now, think about cooking. Why do we boil water or preheat ovens? Because higher temperature speeds things up. In chemistry too, temperature is a major driver of reaction rate. When temperature increases, molecules move faster and collide more forcefully, increasing both the frequency and the energy of collisions. This relationship is captured by the Arrhenius equation, which reads K equals A times E raised to the power negative EA divided by RT, where EA is the activation energy, R is the gas constant, and T is the absolute temperature in Kelvin. Even a small temperature increase can make a big difference. A 10 degrees Celsius rise can double the reaction rate in many systems. A great example is the decomposition of hydrogen peroxide. At room temperature it's slow, but if you warm the solution gently, the oxygen bubbles form much faster. If you look at the energy distribution diagram on screen, you see how the curve shifts to the right, allowing more molecules to overcome the activation barrier at higher temperatures. Let's now talk about catalysts, the unsung heroes of chemistry. A catalyst speeds up a reaction without getting consumed in the process. But how? It provides an alternate pathway with lower activation energy, which means more molecules can participate in the reaction without needing extra energy input. Take the decomposition of hydrogen peroxide again. If you add a pinch of manganese dioxide, that's MnO, the reaction speeds up instantly, even without heating. Why? Because MnO acts as a catalyst. If you examine the energy profile diagram, you'll notice that the peak representing the activation energy is significantly lower in the presence of a catalyst. This means a greater number of molecules now have enough energy to react successfully. Let's move to two physical parameters: surface area and pressure. Picture this. If you drop a chunk of zinc into acid, the reaction is slow. But if you use powdered zinc, the reaction is almost explosive. Why? Because increasing the surface area exposes more reactant particles, leading to more collisions. This concept is critical in solid-liquid reactions. More surface contact means faster reactions. Similarly, in gas phase reactions, increasing the pressure compresses the gas molecules, effectively increasing their concentration, which again boosts collision frequency. For example, in the synthesis of ammonia, nitrogen gas reacts with hydrogen gas. The reaction rate is significantly enhanced under high pressure. That's why industrial reactors are pressurized. If you observe the diagrams on screen, you'll see the difference in molecular spacing and collision frequency in high versus low pressure systems, and in large solid lumps versus fine powders. So to wrap things up, the rate of a chemical reaction depends on how often and how effectively reactant molecules collide. By increasing concentration, raising temperature, adding a catalyst, enhancing surface area, or applying pressure, we can control how fast reactions occur. All of this ties back to the collision theory and activation energy. Only those collisions that are energetic and properly oriented result in product formation. The Arrhenius equation gives us a quantitative way to understand how temperature affects the rate constant, and energy diagrams show us why catalysts are so effective. Whether it's digesting food, designing faster drugs, or engineering better fuels, understanding reaction rates gives us the power to shape chemical change. I hope this session helped you see how reaction speed isn't just about molecules, it's about the hidden levers of temperature, catalysts, and pressure that we can use to control the rhythm of chemistry. Catch you in the next class with more fascinating chemical insights and real-world connections.